Welcome to chapter 5.1 with the extra example found in this section of Math 106. This is example 5 found on page 3. So this is just kind of extra questions that I can ask you given this particular section. So let's say we have an initial population of 100, and I'm going to tack on something a little extra. Let's say our growth constant is equal to 0.077. So can we create an equation? Well, if it's saying that the initial population was 100, that is just saying that P naught is 100. And if we're talking about some sort of growth constant, this is just another fancy way to say K. Now, keep in mind, typically we have the form P of T is equal to P naught e to the KT, in which case we are given everything that we need. We have P of T is equal to 100 e to the 0.077 t. So we're going to be using this formula for the duration of your questions. So when it says how large will the colony be after 41 days, well, P of T is the colony of fruit flies. T is going to be your time, and this will be in days. So if we know that T is equal to 41, and we know that P of T, we can just go ahead and fit that right in. We can go ahead and work that right in. Let me clear that. So 100 e to the 0.077. Actually, I'm going to put that in parentheses. So you'll see we have 2349.9. So let's round that up to 2350. 2350. Fruit flies after that 41-day period. Now let's figure out how fast will the colony be growing at that time. When it says at that time, we're referring to the time from above of 41 days. So if we're saying how fast, right, that is just saying look for a rate or your derivative. So the derivative of P of T, as we've talked about before, we can certainly use your chain rule here, right? Otherwise, we could say, hey, the derivative of P of T is really K times its original P of T, meaning that we have your K, which was 0.077, times your formula that we had been using, 100 e to the 0.077 t. Now, you'll notice that I'm not going to bother simplifying here, but if this is your rate of growth or decay, in our case, it's going to be growth because we have a positive rate here. But now we want to know, okay, what is the amount that it's going to be growing by when it's 41 days? So we can go ahead and work that in. And again, I'm not even going to bother simplifying because that is not our goal. It's just asking us for how fast it is growing. So you'll notice that I have the initial part here, and all I need to do is multiply this value by 0.077. That is your rate. So we have, and I'm going to round a little bit, about 181 or so. So what that value means is that given at 41 days, that your fruit flies are going to be growing at a rate of 181 fruit flies. So after 41 days, the colony is growing by 181 fruit flies per day. Now it says, at what time will the colony contain 800 fruit flies? That is a fancy way to say, hey, if my fruit fly population is labeled as P of T, I want to know if it's 800, what time does that take? And keep in mind what we know about P of T. I'm so sorry, you're going to hear some noise in the background. So let's go ahead and set these equal to one another. We can now go ahead and solve for T here. First thing we need to do is divide by your coefficient. So we have 8 is equal to e to the 0.077t. We need to get your exponent to drop. So let's take the ln of both sides. That'll allow us to cancel. So we have ln of 8 is equal to 0.077t. So t is exactly equal to ln of 8 over 0.077, which is approximately 27 days. So it's going to take approximately 27 days for the population of fruit flies to achieve 800 fruit flies, given that we started at 100 and your growth rate is 0.077. Now let's do one more question. It says, how large is the colony when it is growing at a rate of 200 fruit flies per day? So again, this is saying that this is some sort of a rate. So that means that this is a derivative. This is saying that the derivative of P is equal to 200. We also know that the derivative of P of T, we said was 0.077 times 100 e to the 0.077 t. And we want to know how large that colony is going to be at that particular rate. So we need to actually work backwards. Oh, I'm even better. I didn't even read that question. We know that, notice that the question that I wrote down, if we're trying to figure out how large is the colony, how large is the colony is referring to P of T. And you'll notice that the way that I wrote it, there's no way to fit and solve P of T here. So I'm actually going to scratch that out. Maybe I don't erase it. And instead, I take what I know about your derivative here and say that the derivative of P of T is equal to K times P of T. That is to say 0.077 P of T. So now I have two ideas here. This is that your derivative, right? We have this one here and this one here. We can set them equal to one another. 200 is equal to 0.077 P of T. And now we can go ahead and solve for P of T by doing some sort of quick division. So this is about, let's see, 200 divided by 0.077. So we have 25974. 2957.4. So we'll just round that to fruit flies. So if your rate is growing, and notice that we don't care about the time frame so much, we can try and work backwards, which I'll show you what I'm talking about that here in a second. But if we have a rate of your growth at 200 and we want to know the population, we can go ahead and do a quick division between your values here. Now, the other way, if we were to work backwards, right, You'll notice that when we work backwards, we have 0.077 times 100 e to the 0.077t. You'll notice that you'll have to solve for t. And then when you find t, then you need to plug it in, which isn't bad. It's not always the quickest way to the problem or to your answer. It's still going to work. You just need to do multiple steps. Whereas if you have a good understanding of the derivative and the rate and your constant and all of that together, we can just go ahead and see how much quicker that comes out to be. So that is kind of all of the questions that I could probably ask you in one sort of setting. Um, so that should give you a good edge as to what you might be seeing on your homework, on a quiz, on the test review, and perhaps on your test.